I am your host, Dr. Matthew Richardson, along with my co-host, Joseph Myers, and we are bringing to you today CosmoQuest Astro 101. All right, so I'm going to go ahead and quickly log on to Twitch to make sure that everything is working as it should.
Good, thank you.
If you guys would just bear with us for a quick little second. But how are things going today, Joe?
So far, so good. Got to the office early today and got a little code done. Like I say, right before we got started, I got stuck. But I guess if I'm going to get stuck, that's a good time to do it, right?
Indeed. I'm sure you're not going to be stuck for too much longer.
I got two PhD astrophysicists with me this afternoon. I'm sure we'll figure it out.
I would hope so. No, yeah, I'm pretty sure things are gonna work out just fine. All right, guys, I'm trying to wait to be able to also be able to see chat, but you know what? I can't see it right now. My Chrome browser is taking a crazy amount of time, and it's for good reason. I have a lot of stuff open on my computer for today's stream, but you know what? I'm gonna let that go ahead and just do what it does and move forward with the stream. So, after a lot of thought, a lot more thought than I would have wanted, I was able to finally determine at least a little bit earlier, probably an hour before today's stream, to determine what we're going to talk about today. And it's, of course, is based off what we've talked about in the previous streams. So, I think it's a natural progression to go ahead and start talking about star clusters and how we're able to determine distances in their age, or the distance to star clusters in their age. And what I'm showing here in the background, actually, before I even say it, I'm going to test not only Joe's knowledge but the knowledge of the audience. What star cluster is this that's currently up on the very first slide? Now I know that there might be a lag with what Joe can see, so.
Yeah, I am also forgetting to unmute myself because, like I say, I'm not at home where I'm normally used to streaming. So I think I see a star cluster on the screen here, but I don't recognize it. I don't know. Wait, maybe is that that could possibly be Orion's belt, but I don't know the name of the cluster.
Not Orion. It's not. It's a cluster of stars. Has anyone from the audience given an answer for what this star cluster is, or which star cluster it is? It's a fairly close star cluster. Has a lot of nice blue, bright stars, not blue stars, not blue, yeah, but bright stars.
Same thing.
Indeed. And so this particular star cluster is the Pleiades. And so we're going to be using the Pleiades today for our discussion. And I'm still unable to see you guys' comments. I'm sorry for that right now. Like I said, I have a lot of apps open on my computer, so yeah, the chat's all yours. It's all yours, Joseph.
I got this.
All right. So we're gonna go ahead and move on to the very next slide, telling me to go ahead and go to another app that's open on my computer, Stellarium. So I'm gonna go ahead and switch over to Stellarium here. Nope, that's not Stellarium. Come on, Stellarium. There we go. All right. So, of course, I've already noted that we're going to be using the Pleiades star cluster. It's an open cluster, not too far away from Earth. And of course, one of the objectives of today's stream is to go ahead and calculate the distance to this star cluster. But before doing so, let's just go ahead and see if we can get Stellarium to go ahead and zoom in for us on where the Pleiades is located. So, I'm showing here, of course, a nice little pretty picture of the sun as depicted by the Stellarium application. And so what we're going to do now is we're going to go ahead and shift our view from an image of the sun to where the Pleiades would be located in the sky relative to Earth. To do so, we're going to go ahead and go to the side. Has a bunch of different options. The option I'm looking for, and My computer's going to run probably a little bit slow, but let's see if it'll open this for me. There we go. We're going to go ahead and just go over to the Pleiades. And hopefully my spelling is good. Yeah, there we go. All right. So it's found the Pleiades star cluster. I was playing around with the software earlier and noted the fact that given the location from where I'm viewing the star cluster within the Stellarium application, you actually can't see it in the sky right now. So if I was to put the ground back in, if I'm not mistaken, it would be below the horizon for where I'm currently located at the current point in time. I've kind of set the time to be 12 o'clock a.m., which is p.m. Excuse me, basically local time. And for this location, it's not showing that. Okay, that's cool. Like I said, my computer's running slow, so it probably was having some issues with being able to show the ground. But it's below the horizon for where I'm currently at right now. And what we're going to do, of course, is we can't see other celestial objects in the sky during the daytime. So we're going to go ahead and use our God powers over Stellarium and switch the time to being, instead of 12 o'clock p.m. noon, 12 o'clock a.m. Midnight. To do so, again, go back over to our options, go over to date and time, and simply set the setting to 0. And now that we have nighttime and the sun's, in this case, the light pollution from the sun is no longer an issue, we can now see out into the space to see the Pleiades star cluster, which is shown in the middle of the screen right now. Now, I specifically want to be able to first determine the distance to the Pleiades star cluster. And to do so, really all you need is a star that's actually located within the star cluster itself. To kind of explain a little bit more though, the stars within the star cluster, of course, are at different distances relative to Earth. However, compared to the actual overall distance from Earth to the cluster versus the distance between the stars within the cluster, the distance from Earth to the cluster itself is much larger compared to the interstellar distances between the stars within the cluster. So really you can just take one star and calculate the distance to that star and kind of use that star's distance to kind of define the distance of the overall cluster. So the key thing to note is that in general, stars within clusters, for the most part, have the same distance relative to us. So I'm going to go ahead and, oh no, if you guys can see my cursor, it's giving me the whole little rainbow spinning wheel thing, saying that it's having issues with being able to. I'm sorry, Joe, you say something?
No, I just we don't see your cursor through the
Yeah,
stream. I can tell.
All right. Well, I'm going to go ahead, and I've already selected a star that I want to be able to for us to view, and I believe the star is pronounced. It's actually a multiple star system within the Pleiades star cluster, and it's pronounced the Alcyone. So we're going to go ahead and we're going to do a quick search for Alcyone. Multiple star system. Alright, so now of course the Stellarium program has identified the Alcyone multiple star system, and it's in there, but we really can't see it, right? So we're going to go ahead and go to telescope view. We're going to zoom in, and this is the Alcyone multiple star system. Now again, we've established that in general, stars within the cluster will generally have the same distance relative to us. Well, the same distance relative to Earth. So we're going to go ahead and pick one of the stars within this multiple star system. Specifically, the star that's kind of a little bit up into the left. The first star that's kind of up into the left of the current I think it's a binary or a triple star system that's being targeted right now. So let's see if I can get it to kind of shift. Again, I'm getting that whole spinning wheel. A lot of apps running on my computer right now. But instead of actually just just talking about these things, we're gonna do some calculations today too. Nothing too difficult. In fact, we're gonna go to the internet and let the internet, all the many resources that are available on the internet, to do the calculations for us. But I will definitely, of course, make sure that we are all clear on what's going on with these calculations. And I'm still getting that spinning wheel. So, Joe, has it already updated? Can you see the multiple stars within the system?
What I see is a lot of a mostly dark screen with a lot of information on the left. A small blue circle with like four pretty bright objects in it.
That's it. Yep, that's exactly what I want you guys to see. And so, what we're aiming for right now is the star that is in the middle of this system that we're seeing here. So we got two stars kind of up top, a kind of star in the center, and then a really bright star, or actually a multiple star system at the very bottom. And we're aiming for that star directly in the middle. If my computer will allow us to do it, though. Let's see if it's. Come on, Stellarium. All I need for it to do is allow me to click that star. The key thing that we're looking for here, guys, is to be able to determine well, there's two things you need to know about the star in order to be able to calculate its distance for what we're doing. We need to know the type of star it is, one, and we need to know its apparent brightness, two. But I might just have to just go ahead and just let you guys know what the apparent brightness is. I think I can just barely remember it. And this is actually available. The information is actually available online. If you go to Wikipedia and you were to type in Alcyone, you'd be able to determine what the stars are within this multi-star system. Okay. You know what? The software is not working nicely right now for us. So we're just gonna go ahead and move along to actually calculating the distance to this particular star that's in the multiple star systems Alcyone. Alcyone being a multiple star system that's in the Pleiades star cluster. So to do so, go back to OBS and we're gonna go ahead and bring up a different. Here we go. So earlier I was explaining how we need we need to know certain things in order to be able to calculate the distance to a star. Those things in this case being the type of star, one, as well as apparent magnitude, two. And so going to the screen that's currently or explaining what's currently being shown on within the topic screen right now, what we're looking at is a formula known as the distance modulus. And basically what this formula states is that if you know the apparent brightness of something, as well as its absolute brightness, its intrinsic brightness, you can determine the distance to it. A good example or a good analogy to explain what's going on here is if you were to imagine two people holding identical light bulbs, meaning that they output the same amount of energy. Let's just say that they're two 60-watt light bulbs, and you were to tell them to walk away from you at some random distance. Person A walks away, let's say 10 meters away from you, and then person B walks away, let's say 100 meters away from you. Well, given that the two light bulbs are outputting energy at the same rate, you will be able to notice that there's going to be a distance in the apparent brightness of the objects, all due to the fact that they're at different distances relative to you. And so this equation allows you to be able to take into consideration those different brightnesses, represented here by the lowercase and the lowercase m and the capital M. In the equation, they're kind of showing here. I'm gonna actually highlight the equation. It's actually the distance modulus, but that's the equation, and they've basically taken that equation and kind of simplified it to be able to get a distance. If you can take the difference between the apparent magnitude, or the apparent brightness represented by the variable m, and subtract away from that the absolute or the intrinsic brightness of the object represented by the capital M. And I've already done it. Apparently, this has already been done. What's going on here? I'm gonna go to a different web page. Different web page here. So what we can do is, if Stellarium was working for me earlier, you would have seen that the apparent brightness of the object is 6.25. 6.25 magnitudes. Magnitude is a logarithmic scale that astronomers use to be able to quantitatively define what the brightness of an object is. And the way in which the scale works is, if you have lower magnitude values, or another way of putting it, more negative magnitude values, those particular magnitude values would correspond to an object that's brighter versus a object that has a more positive or higher magnitude value. Simply put, one magnitude one magnitude brightness object is brighter than, let's say, for example, a 5 magnitude object. So the star that I was trying to zoom in on, within the Alcyone multiple star system, has a parent brightness of 6.25 magnitudes. However, to be able to calculate the distance, we need to also know the type of star. And the reason why we need to know the type of star is because specific type of stars that are on the main sequence output energy at a constant rate while they're on the main sequence. That energy output, that constant rate, like for example with earlier how I was talking about, and I looked up really quickly at the light bulb above me, but basically that constant output of energy corresponds to a constant brightness, or in this case, an absolute magnitude. And the absolute magnitude of this particular type of star, this particular type of star being an A0 type star, would be 1.5 magnitude, an absolute magnitude. And this is going to be in the I'm sorry, wait, is that right? I need to also
We
make
got a
sure
question in chat for you, Matt.
let's see.
Larry's asking, what is zero magnitude? That's just, wouldn't that be something to the 0th power, just 1?
So zero magnitude is just indicating that that's the brightness of it, depending on whether you're talking about absolute or apparent magnitude brightness. Is he asking about the difference between the two? What distance?
No, it just says, what is zero magnitude? That's the question.
Okay. So I'm gonna go ahead and try again and make sure I can bring up Twitch. And see if I can see your comments, guys. In this instance, I kind of wish there was something I could do about this, but it's just that my computer just is having difficulty handling all the apps that are open right now. And I need the apps for the stream. But if I understand your question correctly, though, what is zero magnitude? Zero magnitude would just be a specific value of magnitude, just indicating what the brightness of the object is. But it depends on whether you're talking about apparent or absolute magnitude. If you're talking about absolute magnitude, you probably compare the absolute magnitude of that value to a particular type of star. Main sequence star, that is. So what I'm going to do is we're going to go ahead, because all of these values are in the V band. So the key thing about this equation I was showing earlier is that when you take this difference of magnitudes, you have to make sure that the magnitude values are in the same filter. So what I mean by that is, if I'm remembering the filters right, um, it's been a while since I've thought about this, but there's the two filters I'm gonna talk about mainly are the B and V type filters. Um, and what these filters allow you to do is when you're observing a particular object, especially with a telescope, or specifically with a telescope actually, um, the B filter will allow you to observe bluer light, and the V filter will allow you to observe light that's less energetic. Um, and so by taking the by measuring the amount of light a star is outputting at these two different filters, you'll get two different results. But the key thing I'm trying to get at here is that when doing this calculation, this lowercase m minus the capital M, or apparent magnitude minus absolute magnitude for a single star, you need to ensure that that the magnitude values that you're taking the difference of are in the same filter. So I need to make sure they're both in the V filter. So 6.25, and if really, oh, this all sorts of, let's see. Oh, there we go. I think it's 0.7. There we go. So 5.55 is the calculation I'm getting here. And the 0.7 comes from the fact that this is going to be the absolute magnitude of an A0 type star in the V band. And so we get a difference of 5.55. We can take that difference, and if I'm not mistaken, it's 5.58 here. I think I used a slightly different value for the apparent magnitude. It was only off by like I think 0.03, but we can go ahead and use 5.55. And we get a value of a distance in units of parsecs of 128 parsecs. So we'd expect for objects located within the Pleiades cluster to kind of be close to this value, not exact. Remember, they're all at different distances, but close. And so what I'm going to do now is move over to a Wikipedia article that gives values for the Pleiades cluster. Hopefully you guys can also see everything that I'm seeing. I had to reload that page there. And so if we were to scroll down and look on the right hand side of the screen, we'll kind of see that the Pleiades star cluster has a distance of 1.36, 0.2 plus or minus 1.2 parsecs. Now, the value that we calculated for our distance.
Can you control plus a few times? I don't think the viewers can see the text.
They can't see the text. Okay, let me see.
Yeah, at least on my stream, it's too like if you just control plus a few times and beef up that font size, it'll probably be fine.
Yeah, sorry about that, guys. Let's see what we got here. So is that a little bit better? All right. So see, I think for this, and I think the reason why our value is so much lower is probably because of the value that I used. Yeah, I think it should be 6.28. I think I rounded to 6.25, but 6.28 would put this at 5.58. 5.58 would put it here, which is a lot closer to
Hey Matt, Tom Van Scooter's got a question. How do we know the star's type?
Okay, so the stellar type, you'd have to study the star and figure out certain properties, primarily being the intrinsic brightness of the star as well as its temperature. With that information, you can plot it on the HR diagram, the plot that I showed in the previous stream. And I'm gonna show the plot again, but with those two quantities, you can be able to determine what the type of star is. Thanks, Joe, for getting those questions for me, because again, my computer is just completely failing with opening up Twitch. All right.
I'm telling you, man, dual monitors is where it's at.
I'm starting to see that now. I definitely need to get another monitor. All right. And so now that we can kind of see exactly how to be able to. And another thing I want to note though is to get a better estimate of the mean distance to the cluster. Of course, you'd get more stars, measure the distances to those stars, and you'd pretty much average. You'd average the distance to the stars to get an average, a mean distance to the cluster. Okay, so now we're gonna move along, and this is kind of gonna, of course, tie into exactly what Oops, wait, let's do this. You guys can't see the screen I'm looking at. Got to keep up with that. Let's see if I can bring it back. All right, so we're gonna go back to that go to the Stellarium screen, and I wonder did Stellarium even finally allow me to even hit the star? Oh wow, now it wants to work. All right, well that's cool. But yes, since I'm showing it anyway, I'm just gonna go ahead and allow you guys to see. So actually, Stellarium gives. So now Stellarium has allowed me to kind of focus on that star that I was trying to focus on all along. And if you look at the upper left hand corner, Stellarium actually gives an apparent magnitude value of 6.25. The extinction of the magnitude, in the event anyone's wondering, is due to the dimming of the object due to stuff in between the object and us. All right, so let's go back to that topic screen. There we go. All right, so we've all seen this this plot before, and at the very least in one of the previous streams we've seen this plot. This plot is known as, and Joe, do you remember the name of the plot? Can you hear me, Joe?
I can hear you, but I can never find my unmute button. Actually, I don't need it anymore. Everybody's left me in this side of the office alone, so I can just leave it unmuted now.
Okay.
Hirsch Reitzel.
No problem. I completely understand. If you want, you can use the abbreviated version of the name.
Yeah, it's failing me right now.
But no, you're exactly on the right track. So this is the HR diagram. You're exactly right, because honestly, every time I try to like say names for things, I completely like just murder the name, and I feel bad. So I always just use the abbreviated version, the HR diagram, and this kind of gets into the question that the very last question that I just answered. If you want to be able to know the type of star, you need to determine its temperature, and you need to determine its luminosity. By knowing these two things, which if you look at the plot, the y-axis is the luminosity of the star, and the x-axis is its temperature. So by knowing these two quantities, you can plot where that star is at on this HR diagram. And so, this is a nice little pretty picture of the HR diagram, showing essentially all the key things that we know about stars. That is, many of the stars, of course, are going to exist on the main sequence, which is this diagonal line of stars running from the upper left to the lower right of our plot here. In the upper right hand corner, we have our giant stars, and then at the lower left hand portion of the plot, we have our white dwarfs. Well, star clusters are unique in that they're kind of almost like, what's a good way of putting this? They're kind of almost like little galaxies within the galaxy. They're great test beds for being able to understand stellar evolution. And so, if you were to plot, or if you were to take all the stars within a star cluster, you can produce an HR diagram for the cluster itself. And so, what you'd notice, so we're going to move along to this next slide. What you'd notice though is that if you were to able to study the stars within the cluster over some given amount of time, you'd notice that its HR diagram begins to change over time. So when the cluster is initially forming, so the cluster itself basically forms from a giant gas of molecular dust. And so within this giant gas of molecular dust, you have individual stars being formed. So the key thing I want you to take away for star clusters is that one, they all form at the stars within the cluster all form at the same time. Two, their chemical compositions will be the same. Um, and three, the distance, the a rough estimate of the distance to the stars within the cluster is for the most part the same as well. The main thing that's probably different between stars within the cluster is that of course they'll have different masses. All right, so when the cluster first is born or is a newborn, it's put in for the left hand image or diagram within the image. We have an HR diagram for where almost majority of the stars are located within on the main sequence. Sometime later, you kind of begin to see that, oh wait, we're kind of losing some of our really high, massive, really bright stars, bright and hot stars. And the reason being is because, and as we've explained in some of the previous streams, the more massive the main sequence star is, the sooner it will die, because it's outputting a lot of its energy at a much faster rate. So at this moment, they're kind of transitioning off of the main sequence into becoming giant stars, due to the fact that they're no longer burning hydrogen within their core. And so this particular moment where you start to see stars, or the location within the HR diagram where you see stars have branched off and away from the main sequence, is known as the turn-off point. And so what we can do is we can actually use this turn-off point to determine the age of a cluster. And so the logic behind this is that given that stars spend most of their lifetime on the main sequence, if you no longer have certain types of stars present within the cluster, and they were there, of course, at the very start of the cluster, and you know how long it takes for those stars to leave the main sequence, you kind of have a sense of, well, how long the cluster's been around. And so the key thing, of course, you'd want to look at is you'd want to determine, well, where's the turnoff point located within the HR diagram, and you want to draw a vertical line through that turnoff point to the x-axis and determine a temperature. Now, with that temperature, of course, you know that temperature is going to be related to a particular type of main sequence star. And so what you'd of course be able to assume is that, okay, well, given that the current stars that are there are getting within the cluster are getting ready to probably leave the main sequence to become giant stars, and you know how long it takes for those stars to become giant stars, you can kind of get an estimate for the age of the cluster. So what we're going to do now is kind of move along to the next plot here. And this is actually a plot showing the HR diagram, essentially, for the Pleiades star cluster. And again, we're going to go ahead and note what the B minus V magnitude is. And I'm hoping that I probably explained that earlier. Did I explain the B minus V magnitude earlier, Joe? Do you by any chance remember me mentioning that?
I don't think so.
I don't think so.
About two
So
subtract from each other, but I don't think that.
So yeah, that's right. I use that to be able to determine distance, right, of apparent versus absolute. So if you want to be able to determine the temperature of a star, there's a nice relationship between the temperature of the star and the color of the star. The color being determined by this quantity B minus V. So what you'd want to do is you'd observe the star using a B filter, and then you'd also observe the exact same star using the V filter. And you take the measurements you get from these two observations, that is specifically B minus V, to determine that difference. And with that difference, you'll end up seeing that there's a relationship between that and the temperature of the star. I'm going to see if I can actually find There's typically charts, of course, that will show this type of stuff. But what you'd want to do is you'd want to plot b minus v along the x-axis. Determine where the turnoff point is at. Draw a vertical line to that point, and wherever that vertical line hits the x-axis, that will correspond to your b minus v value. And from that, you can determine the corresponding star that b minus v value is associated with. So what I'm going to do now is I'm going to go back. Let's see. So OBS. There we go. We're going to go back to the internet. And we are going to go ahead, and again, I typically would do other calculations myself, but there were time constraints on putting together this particular presentation. So let's see. That is. Oh wait, no. I think I had another idea of doing this, of how to do this. Right, I did come up with another way. So we were going to do some calculations. So we're going to use the lifetime of the stars to kind of get an estimate for the age of the cluster. The way in which we're going to do this is we're going to go ahead and go back to our HR diagram for the Pleiades cluster. Let's see, that's this. Perfect. And so what we're going to do now is we can kind of draw a vertical line for where the turnoff point kind of corresponds to. And what I'm kind of measuring is that the turnoff point is somewhere kind of around, I want to say maybe, and again, I haven't done this, so this is all new to me right now. Well, not all new, I've done this before, but I haven't done this particular calculation for the Pleiades. So we're going to go ahead and look at this plot, and we're going to see that it looks like it has a b minus v value of somewhere around close to 0, maybe that's like negative 0.2, somewhere around negative 0.15, maybe negative 0.15 to roughly 0. So we're going to go ahead and look at what kind of star corresponds to a negative 0.15 star. And so to do this, I'm going to have to bring up another. I want to make sure that you guys can see what I'm looking at here. We're going to bring up another tab, and we're going to look up, let's see, let's look up color of stars. And I'm pretty sure we should be able to find like a chart that shows the different types of stars as a function of their color, or spectral type as a function of color. And then Matt, we can.
Larry's asking a question. He's asking if the turnoff point diverges at mostly the same angle.
If it diverges at mostly the same angle?
Yeah, if it diverges at the same like rate.
Oh, I see. I think I see what you're saying. So, what will end up happening is that you will notice that. Let's go back to. I think I understand what you're saying here. All right, let's go back here, and let's go back to. Where are you? Here. All right. So what you'll notice is that the much brighter and hotter stars, their turnoff point will occur much faster. However, the rate at which the turnoff occurs will slow down as you begin to get to much cooler and dimmer stars on the main sequence. So yeah, the rate will be fast initially for the turnoff, and then it begins to slow down over time. Alright, so let's see if everything is now loaded. And I'm praying it did. Let's see. OBS. We're going to go back here. No, what is going on? Okay, let me think of something that I don't need any. I don't think I need Stellarium anymore. I'm going to cut Stellarium out. It's taking up resources that I need now. So bye-bye Stellarium. We shouldn't need it anymore. And now what I'm going to do is go back to my internet web browser. Let's see if it'll act right. Come on. You can do it. In a few seconds, I'm probably just going to have to just like explain through this. All right. So ultimately what I wanted to be able to do was calculate the lifetime of the main sequence stars that are currently beginning to turn off of the main sequence. Now, of course, to do that with this calculation, I would need to know what the mass of those particular types of stars are in units of solar masses. Now, of course, to get to the particular type, I would need to know what the corresponding spectral type of the star is, and that spectral type is related to the B minus V color of the star. Unfortunately, though, okay, yay, it's there, I'm happy now. All right, so what we're gonna do now is, and I think I could just put color. Let's see, spectral type versus color. Let's see what we get. Pretty sure that there's going to be some plots. Let's see about this. That first one actually looked nice. Come on. Let's see if it'll allow. I'm clicking so that you guys can also see it as well.
Did you not get the click option?
It's I got something there. I'm clicking like crazy here. Actually, what typically happens is if I click on it, it kind of like embiggens it, so it makes it bigger. So I don't know what's going on here. Let's see if this one works. None of these. Okay, so my computer's just still just wanting to run slow. I can scroll still. Oh wait, maybe I can get it from here. Okay. All right. So that's definitely like failing right now. So I think many of the stars within the Pleiades. So when I'm going, oh wait, maybe this might work. All right. These are not giving B minus V values, unfortunately. However, what we're gonna do is this. We're gonna go in reverse now instead. So I have, can you guys see this? Can you see this well, Joe? This current plot?
No, I can't make out any details in it. It's way too small on the screen. So I can see the colors, and I can't even make out the numbers in the colors.
Is that a little bit better?
I don't know. It's probably gonna take a few seconds before I can see it.
Okay.
Yeah. Yeah, I think that will that should do it. I think we can make heads or tails out of that.
So we're gonna kind of work backwards here, guys. So what I'm gonna do is we're actually going to just go ahead and determine what the lifetime of what the current estimate of the lifetime is of the Pleiades, and kind of get what sort of stars are what sort of main sequence stars, what sort of high temperature, high luminosity main sequence stars are kind of still around within the Pleiades. So if we were to go back to the Wikipedia article for the Pleiades, we kind of get an age estimate. Let's see. Let's kind of, oops. Let's do this. That's not right. There we go. Pleiades, come back to me. Thank you. That's perfect. And the reason why I'm doing this, guys, is because The reason why I'm doing this is because my computer's kind of like just not really wanting to work with me the way I want it to work with for me. All right, so it actually it's saying that the cluster itself has a lot of middle-aged hot B type stars, and so given that information, you'd expect for it to have an age estimate going back here for hot B type stars, kind of somewhere within the estimate, kind of from 11 to 400 million years old.
That's a hell of a range.
That is a crazy range, actually.
11 to 400.
And honestly, I don't even know what the Pleiades what the Pleiades clusters age actually is. But the way in which you do it is you'd use the color, the corresponding color for the turnoff point. That color will give you the main sequence stars that are kind of still around or probably in the process of transitioning into becoming giants, and you'd use that age as the estimate of that particular star. Its lifetime estimate for the Pleiades star cluster's age. But I actually want to find out if it's anywhere in here. So if we do let's see, age. That's all it says right now. It's an open star cluster containing middle-aged hot B type stars. But I wanted to be able to go about it another way. Alright, guys. That kind of concludes the main presentation for today. And I'm gonna like kill a lot of things right now so I can be able to at the very least see your comments. So let's get rid of all of this. So let's change OBS. Let's go back here. We can go back to that. I want to kill this so that I can actually see. I'm pretty sure I've probably missed a lot of questions, haven't I, Joe?
No, I think I've got them all to you that have come through so far.
Okay.
That don't mean they won't have more when we're done.
Oh yeah, that's pretty much that's pretty much the conclusion of today's main topic of discussion. Now we're just opening up for questions, because my computer is just having a very difficult time with handling. Let's see. Let's close that. I'm gonna keep this open. I need that. I need this. Yeah, as of right now, I typically use the Chrome web browser to be able to view the chat. But unfortunately, it's just not allowing me to navigate to Twitch. Let's see if it allows me to do it now. There we go. Twitch TV. Are there any questions currently or no?
No, none have come through as of yet.
Okay. Pretty sure I'm probably missing other conversations then.
No, it's been pretty light in chat.
Okay.
They're not really talking to each other either. So.
For the first time, I can now see the Twitch web page. Oh, it is extremely light right now in chat. Oh man. Yeah, Joe, I think I need to like see if I can find, even if it's just an extremely cheap monitor, just something to assist with this, because computer's running really, really slow.
Well, I am in dire need of a restroom break, so should we just call it here?
Yeah, we probably could just call it here because I am not able to see chat at all right now, and yeah, guys. Well, thank you for the viewers that are currently here. Um, Thank you guys for sticking around, and we will see you again on Friday after Daily Space. All right, guys. I'm gonna go ahead and end the discussion here. All right. Okay, bye, guys.